everyone, and welcome to another virtual installment of Astronomy on Tap. So, today we have some amazing speakers to starting off the new year. In fact, happy 2021. So, it's here's to hoping that we have a better year moving on forward. And I hope you have your favorite beverage or drink of preference. For me, it's peppermint tea. I always enjoy a good peppermint tea to relax in the evening. So that way we can toast to the universe. But before I introduce the speakers, I have a couple quick announcements. On February 11th, in the early hours of the morning, just right before sunrise, roughly at 6:55, give or take, if you look towards the east, you'll see the planetary conjunction of Jupiter and Venus. So be sure to check those out. Also on February 18th, we will get to see the landing of the rover Perseverance and the hover helicopter Ingenuity. So tune in to NASA TV on February 18th for this historic event. But now, allow me to introduce to you our wonderful guest speakers for tonight. So first up, we have Anicia, and she is a PhD student at University of Central Florida, but she is a native here in San Antonio. In fact, she's staying here in San Antonio just for the time being. She earned her bachelor's in astrophysics at Wellesley College and moved to Florida to pursue her PhD and to be closer to rocket launches, of course. In her research, she studies NASA's infrared telescope facility to survey primitive asteroids in the asteroid belt and to characterize different asteroid populations. All right, so Anicia, if you could let us see you. Welcome.
Hello.
The floor is yours.
All right, great. So, like we said, like I was so lovingly introduced, my name is Nisa Redondo. I'm a fourth year PhD student at the University of Central Florida. My main research interest is asteroids, particularly primitive asteroids. And so that's what I'm going to talk to you about tonight. I'm part of a group of international collaborators called PRIMUS, which is the Primitive Asteroid Spectroscopic Survey. And so I'm here tonight on behalf of them. So here's a little bit about what I'm going to talk about today. First, I'm just going to let you know what makes an asteroid primitive. What does primitive mean? Then I'm going to give a little brief history about the asteroid belt, its formation, and its evolution. And then I'll get into my own research, which is spectroscopy of primitive asteroid families. So first of all, what makes an asteroid primitive? So in the early formation of the solar system, before we had a solar system, there was just a big cloud of gas and dust, and that's called the solar nebula. It became a disk because of angular momentum. It flattened into a disk, and the elemental composition of this disk was mostly hydrogen and helium, but there were some amounts, lower amounts of lower amounts of other elements like carbon, oxygen, nitrogen, etc. So this plot on the right shows the abundances of elements in the solar nebula. Eventually, planets started to form, and then over time, obviously, the chemical composition of our planets has changed. So here is the chemical composition of Earth currently. You can see there's pretty much no helium left. And yeah, neon's gone. It's very different than the solar nebula. And so primitive asteroids are so great because they formed when the solar system formed. They have been mostly unaltered since that formation, which means that they maintain the same composition as the initial solar system. So by studying primitive asteroids, we can study what the solar system was initially made of. And so they're called primitive because they are made of the most primitive, oldest material in the solar system. So during the formation of the planets, like I said, there's this big disk of gas and dust. The sun is at the center, and then the dust starts coalescing into these rocky bodies. And so that's what all these primitive bodies are. And so visualized with Legos, primitive bodies are like one pieces of Legos, and then gravity pulls them together to make these kind of bigger planetesimals. And then gravity pulls those together to eventually form planets. And so that is why we call primitive asteroids the building blocks of the solar system. And so after the planets formed, everything that was left over is what the asteroids that we currently see today. So now I'm going to go into a brief history of the asteroid belt. So in our solar system, we have the sun in the center, all of the planets. Between Mars and Jupiter is where most of the asteroids in our solar system are. It's called the asteroid belt. And so when the belt was forming, things that are closer to the sun have different compositions than things that are further from the sun, because the closer things got heated more because they're closer to the sun. So the inner edge of the asteroid belt, this is very simplified, by the way, because I'm not a dynamicist, but the bare gist of it is that the inner edge is very hot, and so some rock can melt. So a lot of the inner asteroids will have like iron, and they can differentiate even and be layered, kind of like the Earth has an iron core. Some asteroids actually differentiate like that as well. Where in contrast, the outer edge is really cold, and so asteroids in the outer edge, ice can form on them, and that will, ice forms on them. And then something happened, and this is way outside the scope of my work, but there was a large scale mixing event, probably caused by the giant planets kind of moving around closer and farther from the sun. And so what ended up happening is that the inner and outer asteroids are now mixed throughout the asteroid belt. And so when the icy outer belt objects moved into the inner belt, the ice on them melted. And this is called aqueous alteration. What happened is the material that was already there got touched by water, and then it formed phyllosilicates. And so phyllosilicates is just a fancy word for hydrated minerals. And why do we care about water? Well, for one thing, the Earth is about 70% water. And as far as we know, liquid water is a big requirement for life. And so understanding how water got to Earth is really important to understand how water can get to other planets and other systems. The leading theory is that most of Earth's water was actually delivered by hydrated asteroids. And so understanding the water abundance and the distribution of asteroids in the asteroid belt can kind of help us to understand what's going on, what went on in our system, and what's going to go on in other systems that we can observe. So I'm going to take a drink for a sec. Since the mixing event, a lot of time has passed. That was in the way beginning of the solar system. And in the asteroid belt, there's a lot of asteroids, and sometimes they collide. So here's two asteroids that are moving towards each other. Boom, they hit each other, and the result is a bunch of fragments of smaller asteroids. And so when the asteroid breaks apart, the asteroids actually stay really close to each other. The fragments stay really close to each other, and they're made up of relatively the same composition because they came from the same parent body. And so we call groups of asteroids like this an asteroid family. And then the one that broke up is called the parent body. And asteroid families are basically what I do. So this here plot is, it shows the distance from the sun of all of the planets compared with the inclination in the plane of the solar system, which is basically just all of the planets orbit in a plane, but some of them are kind of higher than the plane is, and that's what inclination is. And so between Mars and Jupiter, I have plotted all of the primitive asteroids in the asteroid belt, and you can see kind of, I don't know if you can see my mouse, but there's some clusters of asteroids that are really close together, and those are actually asteroid families. And so in my research, what I do is I look at these asteroid families and I try to characterize them, and I try to see if they're similar or different from each other, and what's going on, how the asteroid belt is made up. So my main technique that I use is called spectroscopy. When sunlight reflects off of an asteroid, it comes back to us in multiple different wavelengths, the light does. And certain materials If they're on the surface, they actually absorb some of the light. And so at a certain wavelength that corresponds to a certain material, light won't get reflected back. And so if you get a spectrum, a reflecting spectrum back, and there's light missing at certain points, that can tell you kind of what the asteroid is probably made of. So in this right plot, I have two examples of asteroids. The blue one, asteroid spectra. The blue one is not a primitive asteroid, and the orange one is a primitive asteroid. So in the blue one, you can see these two dips right here. Those are called absorption features. They're at about 1 micron and 2 micron, and those are indicative of iron-bearing silicates. So it's not a primitive asteroid because it has iron on it. If you look at the primitive spectrum, the orange one, it's a lot less, there's a lot less going on. You can tell less from it just because there aren't as many features, but there is actually a very shallow absorption band here at 0.7 microns, which is indicative of phyllosilicates, which, as I said earlier, is indicative of hydration. So visible, if we take visible spectroscopy of asteroids, that can tell us about hydration in the asteroid belt. So here's our primitive spectrum. The visible portion of the spectrum is here between 0.4 and about 0.9 microns. And we look for the 0.7 micron feature because that tells us about hydration. Here's the plot of all the families again. And what we did basically was take observe a representative sample in the visible of all of these asteroid families, and we searched for the 0.7 micron feature. And what we found is a wide variety of hydration levels. So like the Polana, Clarissa, and Svea families are all pretty much not hydrated at all. Aragone and Sulamitas families are about 60% hydrated. The Clio and Chimera families are about 20% hydrated. And then the Chaldea family is the most hydrated. It's almost 80% of the whole family shows this 0.7 micron feature. And so if we take the left plot and instead of, if we change the color scale to just amount of hydration, where the darkest green is not at all hydrated and the darkest blue is very hydrated, you can see that there's not really a pattern to this. It's not a gradient. And that kind of just tells us that the asteroid belt is very well mixed. There's not really rhyme or reason as to why certain families are more hydrated than others that we know of yet. So visible spectroscopy can also tell us about the composition of the parent bodies. So some of the things that we can do to spectra is measure the spectral slope, which is basically if this blue line is a spectrum, the orange line is a slope. It's just like algebra class slope. And so here is a histogram of spectral slope for two different families. And you can see that the Polana family has a very small range of spectral slopes. It goes from about, -3 to 3. And that kind of tells us that the parent body was homogeneous because all of the asteroids pretty much look the same. Whereas the Aragona family, the red lines have a wider range of slopes. It's almost double the amount of slopes. And that tells us that the parent body was heterogeneous. There's different compositions within this one body. So besides visible spectroscopy, there's also near-infrared spectroscopy. Near-infrared region is from 0.9 to about 2.5. And this is more of what I have done in my PhD research. As you can see, there's not a lot going on in this spectrum. Most primitive asteroids don't have any absorption features at these wavelengths. And so really what you do to characterize these are look at spectral slope. So this is the average spectral slope for two different families, the Clio and Sulamitas family. And as you can see, the line is the average and the shaded region is plus or minus 1 sigma from the mean. They're essentially the exact same. And that was really a surprising result because in the visible, if you remember, Sulamitas was like 60% hydrated and Cleo was about 20% hydrated. And they're also very far from each other in orbital space. And so that led us to conclude that the near infrared isn't really diagnostic for primitive families to distinguish between them. We did find one statistical difference in the near infrared spectroscopy, which is with curvature. So on this plot, I have it's the average spectrum for the Chaldea family and the average spectrum for the Polana family. And as you can see, the Polana family is kind of convex shaped. It's smiley. And the Chaldea family is concave. It looks like a frown. But as of right now, we don't completely understand what causes differences in curvature. That's something that I'm currently researching. I think it might have something to do with space weathering, but you'll have to ask me in about a year what's going on there. So when we combine the visible with the near infrared, then we can really understand things more. So one of the things that I'm really interested in looking at is the background population of asteroids. So if all of these colored dots are families, all the gray dots are not families, which means that they're background objects. It's about 56% of the inner asteroid belt are not assigned to any family. And so what I did is I split the background into 3 different groups. One of the groups was right here around Polana and Clarissa. One of the groups was here around Aragona and Sulumitis. And then one of the groups was here around Cleo and Chaldea. And what I did is I compared the visible and near infrared spectra of the background asteroids in each group to the family asteroids in each group. And what I found is that the background and the families are similar in composition. So that kind of suggests that the families in the background may come from the same source. And so what I mean by that is take the Polana and Clarissa families, for example. If there's one parent body at the start of the solar system, that eventually broke up into a Polana parent, the Clarissa parent body, and then a bunch of background asteroids. And then, I don't know, a couple billion years later, Polana broke up into the Polana family and Clarissa broke up into the Clarissa family. And then now those are the distributions that we have seen, that we see today. And so this idea of kind of like grandparents of families is something that I'm really interested in looking at more. It's still very much in the works, but there is a hypothesis out there that asteroids formed big. And this work that I've done here kind of, well, no, it doesn't kind of, it definitely is evidence for that hypothesis. So in summary, primitive asteroids are the building blocks of the solar system because they're made of the same material as a solar nebula and because planets formed from them. I use spectroscopy to infer the composition of asteroids and to compare between populations of asteroids, particularly between the families and the background population. And in my work, I've found that primitive inner belt asteroid families have varying degrees of hydration, which tells us that the asteroid belt is well mixed. They have very different ranges of spectral slopes, which shows us that the parent bodies were not completely homogeneous as previously thought. And the families have similar composition to the background population around that area, which indicates that the background and the families may come from the same source or these grandparent bodies. Thank you.
All right. Thank you for that wonderful presentation. I enjoyed it. It was very engaging, and I loved the idea of using Legos as your basis to be able to explain such a complex topic. So thank you. All right. So, folks, if you have any questions, leave it in the chat, and I would be happy to relay the questions to our amazing speaker. Oh, and we got a couple right off the bat. So the first question, it's a 2-part question. How do you know exactly which asteroids belong to a single family, and how many different families are there in the asteroid belt?
Yeah. So determining family membership is something that dynamicists do, and I'm not at all a dynamicist, but basically what they do is they use orbital elements, so semi-major axis, inclination, and eccentricity, and they combine that with information about like diameters and albedos. And using a lot of math and codes and stuff, they have a certain threshold um, value for this clustering method, and that kind of that's how they determine family membership. But it's kind of it's like an art form, I would say, because if you change that threshold a little bit, then you get either more or less family members. And so it's not an exact science by any way, but it is like the best um, way we have to determine membership. Um, as for the number of families in the asteroid belt, I'm not sure about the entire asteroid belt, but in the inner asteroid belt, which is the part that I focus on, it's about the inner third of the asteroid belt, there's 20 families.
Okay. And they have a follow-up question. To clarify, the three background populations all look similar to one another. And the background look the same in the asteroid families?
The background of the whole belt looks different from itself, but if you look at the background just around each family, that looks similar to the families.
All right. Another question. Hi, Anicia. It's Terry from San Francisco. Thank you for your presentation. Can you explain to us your thoughts on, I am probably going to mispronounce this because I know it's a Hawaiian name, the Aoumuamua, our recent interstellar visitor?
um, my
Oumua. I know it's
yes.
Hawaiian, and every time I hear it, I've mispronounced it several times. I just, it's difficult for me.
Well, okay, my thoughts on it are that it's really cool. I definitely don't study it. Um, I know it's interstellar. I know it's from somewhere else. I don't have much more information than that.
Question. Which telescope do you use for your data collection?
I mostly use the NASA Infrared Telescope facility, which is on Mauna Kea in Hawaii. But I also, some of my foreign collaborators use the Telescopio Nacional Galileo, which is in Spain, La Palma, Spain, in the Canary Islands.
Next question. Can you figure out the asteroid age or how long ago it was broken apart based on its composition slash spectral slope?
So yes and no. The way that you would tell an asteroid age, well, if you physically go and get a sample and do spectroscopy, like OSIRIS-REx just took a sample and it's going to bring it home, and then people in their labs are going to do spectroscopy on it, and they will definitely know the age of that asteroid. Um, from the Earth to space, probably not. The way you would get an age is that you would actually use dynamics. You plot the size of asteroids versus their semi-major axis, and that's going to tell you how far they've drifted in their lifetime. And that's directly proportional to how old they are. So larger drift in a family means it's an older family.
Okay. Next question. Where would you group the asteroids that don't have strong reflectivity and are difficult to get a spectrum for?
So I did not mention this, but primitive asteroids are extremely hard to get spectra for because they're actually really dark. Most of them are darker than charcoal. And so the amount of light they reflect back is not a lot. Um, so where would I group them? I'm sure there's many that we don't even know exist just because they are lower than our detection limits. But if their orbital elements are similar to the families and their albedos are similar to the families, then they should be grouped with the families.
All right. Next question. Are you able to look at these asteroids in the ultraviolet?
I wish I could look at these asteroids in the ultraviolet. Um, I personally don't have any access to any type of UV telescope, but I know Tracy Becker at Swarry does, and it's really cool. It's a really great project. Not a lot of people look in the UV at asteroids.
Tracy Becker always has the best equipment. Next question. Is it possible that the parent asteroid was large enough to be considered a planet?
Good question. Yeah, probably not, because so even the largest asteroids are still, I think the largest asteroid is about 1/3 the size of Texas. Um, Even whatever that asteroid's parent body was is probably also going to be really, really tiny in the grand scheme of things. So no, probably not.
All right, next question. How quickly do asteroids move past a visible collection, and how often or how long can you measure or observe them?
Oh yeah. So this is something that I definitely have to think about with this is a really long observing campaign that I've done. I've observed over 100 asteroids, and there were definitely times where I had telescope time, but there was nothing up to look at, and that's extremely frustrating. So it depends on their orbits. If they are the best time to observe them is when they are closest to the sun, because that's when they're the most illuminated. It's called opposition, and that's when they're the most illuminated, easiest to see. You get great data, awesome. Um, but because of their orbits, some of these things are only up for a month a year. And so you doing an observing campaign like this, you really have to plan it out and make sure that you are asking for telescope time on times when there are objects up.
All right, next question. When you say that a family is 50% hydrated, does that mean that 50% of the surface is water, or is it a blob of half water and half rocks floating around?
So yeah, I guess that was a little bit misleading. When I say hydrated, I just mean there are hydrated minerals on it. I think the most hydrated asteroids are only like 2% water. It's not a lot.
All right, next question. Are there any plans for NASA to explore any asteroids from a specific family? And which family do you think would be the most interesting to explore?
Ooh. Um, I I don't think there are. So NASA currently has a mission. The Lucy mission is on the going to be on the way to Trojan asteroids, which aren't part of a family, and then the Psyche mission is on its going to be on its way to Psyche. Um, but I don't know of anything else. I think so. I think the coolest family to see an asteroid from is the Polana family, and that is because it's the largest primitive family in the inner belt, and the inner belt is the main source of near Earth asteroids. And so near Earth asteroids are cool for a number of reasons, mainly for me at least, is because they could kill us. Um, but by studying their origins, then we can know more about like how to mitigate this hazard. And the Polana family is definitely the parent family of asteroid Bennu, which is where Osiris Rex just took a sample from. And so I think it would be really cool to have that sample and then directly compare it with its family. That would give us a lot of information about meteorite and asteroid links.
All right, next question. In your spectroscopy, do you have to account for absorption via interplanetary materials such as dust and all the junk in our solar system?
um, I don't. There are some people that do. It kind of depends on what wavelengths you're looking at. Um, so if you the biggest hindrance to spectroscopy, I would say, is actually the Earth's atmosphere. And so if you go to longer wavelengths past the infrared, you get to the mid infrared. That's where the atmosphere is absorbing a lot. And so that's kind of what is a greater hindrance to spectroscopy than interplanetary dust.
Next question. In your opinion, what is the coolest part of your research?
By far, the coolest part of my research is using telescopes. I love telescopes. I love the science of telescopes. I love using them. I love feeling like, I could break this billion-dollar machine in a second if I mess up. It's just really fun to stay up all night and just stare at a computer screen.
All right, are there any other questions? All right, if there are no more questions, thank you so much. And we will now let our next speaker, Kevin, take the floor and allow me to properly introduce him. So Kevin Delano is a fourth-year PhD student at UTSA, and he does research at SWRI with the Earth's magnetic field. And he's earned his bachelor's degree at Lafayette College in Easton, Pennsylvania in 2017, and now he's moving on to work on his PhD. So Kevin, the floor is yours.
All right, thank you very much, Michelle. Let me go ahead and share my screen and make sure everything comes up correctly. Everything looks good so far?
Yes, sir, the floor is yours.
Perfect, thank you very much. All right, well, as Michelle said, my name is Kevin. I am a UTSA graduate student in the joint UTSA Southwest Research Institute Space Physics program, and I study space plasmas. And today I'm going to be talking about how solar wind impacts Earth's magnetic environment. So here is just a brief outline of what I'll be talking about today. I'm going to start by talking about the solar wind, just kind of what it is and why it's important. Then I'm going to do the same thing with Earth's magnetosphere, what it is, why it's important. And then I'm going to move into the interaction between those two things. And I'm going to focus on a process called magnetic reconnection. And I'm going to talk a little bit about why that's important and how that has an impact on us as humans. And then finally, I'm going to talk briefly about my own research, how I study space plasma interactions at the magnetopause. And then I'll finish with a summary. So I thought a fun place to start for this talk would be a Star Wars quote, because, hey, why not? So in episode 9, there is a scene where I think, yeah, it's Poe and Rose and Finn are talking about all the dangers of trying to get to Exegol, which is this, very mysterious planet. And, somebody says it's a mess out there. There's magnetic cross fields and gravity wells and solar winds. And of course, as a space physicist, I had to laugh because, you would think that in a society that's figured out how to do hyperspace travel, solar wind just wouldn't be an issue, right? Well, as it turns out, solar wind is actually something that's very important, and it has some very visible effects that, just regular people that like you and me can experience. I'm also going to talk a little bit about magnetic cross fields too. I think that was one thing that JJ came up with. He's really good at coming up with things that don't really make sense and just, trying to make it work. But it turns out he actually got kind of close with that one. So I'll talk about that a little bit. So let's start with the solar wind. What is it? Well, the sun, in addition to constantly emitting light, is spewing out a plasma called the solar wind. Now, that begs the question, what is a plasma? Simply put, it's a charged magnetized gas. And when I say charged, I mean that it's made up of ions and electrons. And magnetized, meaning that any plasma has its own magnetic field. So you can think of a plasma as a type of fluid, like water or air, just with a magnetic field. And yeah, that's what I mean by plasma. I guess the other thing I want to mention about solar wind is that it's about 95% protons, also known as hydrogen ions. So your normal hydrogen atom is just a proton with an electron orbiting it. You take away the electron, you're left with the proton. And that's mostly what solar wind is. It's almost all protons. But the next largest species in there is something called alpha particles. And an alpha particle is 2 neutrons and 2 protons together. Another name for that is helium double plus. It's a helium ion that's been fully ionized. And then, of course, there's some small amounts of heavier ions as well in solar wind. And they're pretty interesting too, but I'm not going to be talking about those today. A couple other things I want to mention about solar wind. So this is just something to hang on to. I'll talk about this a little bit later, but as I said, plasmas have a magnetic field associated with them. And for the solar wind, the interplanetary the magnetic field that's associated with it is something we call the interplanetary magnetic field. So hang on to that. I'll talk about that a little bit later. But the main thing that I want you to get from this slide here is that solar wind is extremely sparse, but it's very energetic. So on average, solar wind, the number density of solar wind is 5 particles per cubic centimeter. So 5 whole particles in a single cubic centimeter. And to put that in context, if you're looking at a cubic centimeter of air, that has 2.5 times 10 to the 19 particles in it. That is, let's see, 10 to the 19 is 1 trillion times 10 million. So it's just a huge difference. Solar wind is extremely, extremely sparse, but it has a lot of energy. And as a matter of fact, on average, solar wind moves at 450 kilometers per second. Now that's not a typo. That's not kilometers per hour. That's kilometers per second. And if you were traveling that fast, you could get from here, San Antonio, to where I graduated from college, Lafayette, in about 4 or 5 seconds. And for you local folks, you could go from San Antonio to Dallas in basically 1 second. So that's moving. That's pretty fast. So now that I've talked about the solar wind, let's talk about the magnetosphere. So what is it? Well, as you know, the Earth has a magnetic field, and it turns out that the Earth's magnetic field is strong enough to resist the solar wind. And as a result, you get kind of this bullet-shaped barrier around the Earth. And the region that's enclosed by that barrier is called the magnetosphere. And then the barrier itself is something called the magnetopause. And I have a diagram here on the next slide. So as you see, on the left is the solar wind. You can't exactly, well, this figure doesn't show it, but you can just imagine on the far left side, outside of the frame, is the sun. And the sun is emitting the solar wind. And then on the left side, you have the Earth. And if you're looking at those pink lines right there, those are something called magnetic field lines. Now, magnetic field lines aren't real in a sense. They're not something that, it's not a physical object, but what they do is they're a representation of how the magnetic field exerts a force on charged particles. So as I said before, the solar wind, it has its own magnetic field coming along with it, and the Earth has its magnetic field, and there's a barrier that separates those two magnetic fields, those two plasma populations, as it were. And that barrier is called the magnetopause. And you can see that that's kind of the furthest pink line right there. So that's the magnetopause. And now I want to talk about magnetic cross fields, sort of. Well, as I mentioned, JJ likes to come up with random things, and magnetic cross fields is one of them. But as it turns out, it is kind of close to something that's actually real, because there's a process called magnetic reconnection. And the way that you start magnetic reconnection is you have two opposed magnetic fields. So if you look at the diagram at the bottom of the screen, this is taken from one of my advisor's diagrams. If you look at the leftmost panel, panel A, you'll see you have green magnetic field lines pointing up, and you have this gray separator. In this case, that would be the magnetopause. It's labeled plasma current layer. And then on the right, you have orange magnetic field lines pointing downward. And this is the starting point for magnetic reconnection. And one of the really interesting things is that in space, when you have magnetic fields pointing directly opposite to each other, when you have two converging plasma populations, they tend to come together and annihilate. And this results in this explosive process called magnetic reconnection. So moving from panel A to panel B in the middle there, you'll see two arrows, and that represents plasma inflow. And you start to see how the magnetic fields start to bend a little bit. And there's this X-shaped region in the middle called the diffusion region. And that's where some really interesting and complicated plasma physics happens. But basically, what you get is magnetic field lines splicing and then reconnecting, which is crazy. And then ultimately what you have in panel C there is what's labeled magnetic slingshots, more commonly known as particle jets. So particles come in, they're demagnetized as they come into the diffusion region. They get reconnected onto new field lines, and they get shot out in opposite directions in those plasma jets or the slingshots. It's a really neat process. And it's responsible for a lot of really cool stuff that happens at the magnetopause. And that's what I'd like to talk about next, why reconnection matters. So as I mentioned, magnetic reconnection is responsible for a change of magnetic topology. And that mainly has two major effects at the magnetopause. So first, it allows solar wind to enter the magnetosphere. If there were no reconnection, the magnetopause would just be this solid barrier that keeps solar wind out, and solar wind would never be able to get in. But because of magnetic reconnection, solar wind can enter directly, as plasma that gets demagnetized and just comes through and gets shut out through the jets. Or it also changes the topology of the magnetopause so that you can get some diffusion across it. And then the other thing that reconnection does as a result of that explosive process is a transfer of magnetic energy. And this is key right here, because this means that magnetic energy can propagate from the sun, come to the Earth, through reconnection, energize Earth's magnetic field and change it a little bit. So you may have heard of something called coronal mass ejections. That's a very large outflow of solar wind and magnetic energy that comes out from the sun. Those can be dangerous because that magnetic energy in the CME through reconnection gets transferred to Earth's magnetic field. And that changes the magnetic field topology a little bit. So why is that a big deal? Why does it matter if the Earth's magnetic field gets shifted a little bit? Well, when a magnetic disturbance reaches Earth, it's called a magnetic storm. And I'm not going to talk about all of the processes that go into it, but one of the positive things that happens is you get the auroras. So as an example, in 2003, around Halloween, there was a really large magnetic storm. And in my town of Columbus, Ohio, you could actually see the northern lights because the magnetic storm was so powerful that it energized so many ions in Earth's magnetosphere that not only could you see the aurora, at far northern latitudes like Finland, but you could see it all the way down in Columbus. So that's one thing that magnetic storms do. The other thing that they can do, it's not quite as fun, is you can get, when you have a changing magnetic field, you can get current flowing in places that you don't want to. So for example, there was a power outage in Sweden for the same 2003 Halloween event, where Earth's magnetic field just was shifted a little bit. And as a result of that shift, that induced a current in a transformer that blew up, and it caused a power outage in Sweden. And things like that have happened before, and they will happen again when we have magnetic storms. So the point I want to impress upon you there is solar wind and the interaction between solar wind and Earth's magnetic field has some very real effects. This is not just something that's theoretically interesting. It's something that we can see the effects of, and it's something that we can't just ignore. So now that I've talked about that, I want to talk a little bit about my research. So what I do is I study the intricate details of how the solar wind and the magnetosphere interact. And it's a very complicated system. I just kind of gave you a very large scale overview of what happens and the most important process, magnetic reconnection, but there's also other ways in which they interact. And the way that I do this is I study data from the magnetospheric multiscale satellites. For short, it's MMS. And as you can see, I put a picture of one of the papers that I've published, and that's kind of a mouthful. So I'm not going to read that. I'm just going to go ahead and explain it in a different way. So when solar wind particles approach the magnetopause, this is away from a magnetic reconnection site, they do one of two things. They either pass through or they're reflected back towards the sun. So if you look at the diagram on the right, you see solar wind coming in. That orange barrier right there is the magnetopause, and either they pass through into one boundary layer or they're reflected and there's another boundary layer there. So for my project, what I did was I used measurements from MMS's plasma instruments, and I determined whether or not H plus and He double plus, so those were the two primary ions in solar wind, under certain conditions are reflected at the same rate. How did I do that? Well, what MMS does is it orbits the Earth in a very oval-shaped elliptical orbit. And it goes out far enough that it crosses the magnetopause at least twice on each orbit. I say at least twice because as it happens, the magnetopause tends to shift a little bit. It moves back and forth. So as the satellite is going out, for example, the magnetopause might move back and forth as the solar wind pressure changes. But that's just kind of an aside. Nonetheless, MMS observes a ton of magnetopause crossings. And what I did, looking at those magnetopause crossings under certain conditions, I looked at the relative helium double plus concentration in boundary layer 1 and boundary layer 2. And if I saw that they were the same, that means that that is, if the relative He double plus concentration is the same, that means that both H plus and He double plus are reflected at the same rate. If they were different, that would mean that it was not reflected at the same rate. And as it turned out from the statistical study that I did, the answer is yes. It turns out that H plus and He double plus are reflected and transmitted at the same rate. So why is that important? Well, as I mentioned earlier, plasmas are responsible for carrying a magnetic field. And so in order to understand the magnetic field, you have to understand the composition of the plasma as well. So it's important to know what's getting in to the magnetosphere and how it's getting in. So my research was kind of a small part of that, but yeah, just kind of a small piece of the puzzle to understanding the large scale dynamics of the magnetosphere. All right, so just a brief summary of what I've talked about today. These are the things that I want you to take from my talk. First of all, excuse me, solar wind is a plasma emitted by the sun. Because Earth has a strong magnetic field, it has a magnetosphere around it that protects it from the solar wind. However, pardon me, the solar wind and the magnetosphere interact. And one of the primary ways that that happens is through a process called magnetic reconnection. And reconnection is responsible for injecting energy into Earth's magnetic environment, and that sometimes results in a magnetic storm. And then the last thing, sorry, excuse me. The last thing I want to talk about, or the last thing that I want to mention, is that space science is a relatively new, exciting field. We're constantly learning new things about how space plasmas interact. And it's something that's going to be relevant for the future. The more that we want to go up in space, the more that we want to explore space, the more that we rely on satellites, the more, this is crazy. Needed a drink there, sorry. The more that we're going to need to understand how space works. And that's what space scientists do. So with that, I will close and answer any questions you might have. Thank you.
I love your Star Wars references. It's just so fun to watch them. And I know I've done videos on explaining why Hollywood can't do science. As I always say, Hollywood's theme is fake it till you make it, and they do it very well.
Yep, that is true.
All right. Are there any questions for Kevin? Any questions at all? All right. A couple right off the bat. Can you predict when magnetic storms will occur?
That is a great question. To some degree, yes. We have what are called upstream solar wind monitors. So, for example, one of those satellites is called ACE, and that can kind of measure just kind of the magnetic field, the strength of the magnetic field in the solar wind, and also the number of particles in the solar wind as well. And if we see an increase in, my goodness, sorry.
You need to take a drink. Go ahead.
Yeah, my apologies. Well, unfortunately, I actually caught coronavirus a little over a week ago, so I'm still recovering a little bit. I apologize for
sorry.
my lungs, but I'm doing fine. So yes, the upstream solar wind monitor. So we can measure those things, but it's not something that we know until kind of the last second. We also don't know necessarily how bad it's going to be. We might know a little bit if a magnetic storm is going to be really strong, but we don't really know. And that's one thing that people are working on, kind of the field of space weather and how to predict when a really big magnetic storm is going to come along.
Josh Quasia says, "Get well soon," and great presentation.
Thank you.
Next question. What about the Van Allen belts? I thought they reflected the solar wind.
So that's something interesting. I don't study the Van Allen belt all that much, but if I remember correctly, and I might be wrong here, the Van Allen belts are primarily responsible for reflecting cosmic rays, not so much the solar wind. I don't quote me on that, but cosmic rays are something else entirely. That has to do with extremely energetic particles, sometimes from outside of our solar system, that come in. So yeah, I think that is primarily what the Van Allen belts protect us from.
Got it. Next question. Are you involved with the proposed Punch mission through SWIRI?
That is a very good question. I am not, but one of my advisors is. Heather Elliott is heavily involved in the Punch mission. So if you want to know about that, I would talk to her.
Next question. How many orbits did you use in your study, and what percentage of MMS orbits was that?
Good question. I don't know the percentage of total MMS orbits. That's kind of an interesting question because it used to be that MMS would orbit, do a full orbit in about a day. Now they changed the orbit so that now it takes longer for MMS to orbit. So I looked at events from what's called MMS's phase 1A mission. And so that was in late 2015 and early 2016. And I looked at about, let's see, I looked at over 200 separate magnetopause crossings by MMS. And then I had a certain set of selection criteria that I applied that whittled that down to about 40 good events. So I was looking at 40 good crossings that satisfied all the criteria that I was looking at, and I used those to do my statistical study.
Okay. What would happen if the Earth did not have a magnetic field? That would be good. I know for that.
Yeah, that would really not be good. And we might, depending on what the pole shifting does, we might get to experience a little bit of that. But as I said, Earth's magnetic field is kind of Earth's defense system. It keeps out a lot of dangerous particles that come in. So if you want to think about, what it would be like, without a magnetic field, you might think about a place like Mars. Mars does not, it has just a very small magnetic field, but it's just barely there. So if you can imagine how, barren Mars is, I don't know if any of y'all have seen The Martian, but if you look at the scene, towards the end where like he just kind of has all these sores all over his face, that's just from, radiation exposure. Because Mars doesn't have a magnetic field. It also doesn't have an atmosphere as well, and that plays in a little bit to it. But magnetic field is definitely a good thing here on Earth.
All right, next question. How can we protect ourselves from negative impacts of magnetic storms?
Turn the power off. I guess that's the simplest answer. I do know there are, some contingencies in place, particularly for satellites. I think at this point, if we can get any warning at all, that's a good thing. And, satellites can just turn off. But yeah, other than that, I don't really know. I think that's something that people are looking into and trying to figure out a way to mitigate the effects.
Veronica Garza says she loves your Star Wars references and hope you feel better after having a drink of water or something. And well, next question, what happened to the electrons in the solar wind? You said the solar wind is 95% protons.
Good question. So it's 95% by mass. I don't know. I don't think I mentioned it, but electrons are about 1,000 times smaller than protons. So by mass, the solar wind is 95% protons, 5% on average, alpha particles. And the electrons are there too. One of the other things about the solar wind is that it's overall charge neutral. So for every proton, you have an electron. And for every alpha particle, you have 2 electrons because alpha particles are doubly ionized, He2+. So the electrons are there and they're very important. But I mostly study ions. So that's why I talked mostly about the ions today.
All right, next question. Where are the slingshot effect? At the poles or where the plasmas are close to each other?
So, yeah, I guess let me go back to that slide. Maybe I didn't explain that all that well. So the jets are perpendicular to the direction of plasma inflow. So if you look at panel C, on the left-hand side, you have an arrow pointing inward to the right. And on the right-hand side, you have an arrow pointing to the left. And those represent the inflow direction. That's where the plasma comes in. And it depends on where magnetic reconnection is happening, right? Reconnection happens at a bunch of different places on the magnetopause, but the jets always shoot out perpendicular to the inflow region.
All right, next question. What are some of the other ways we study our magnetosphere and its interaction with the solar wind?
Good question. So obviously the electrons are important. I study ions mostly, but there are instruments on MMS that study the electrons as well. The diffusion region, as a matter of fact, in panel B right there, there's actually 2 different diffusion regions. There's one for the ions and there's one for the electrons, which are a little bit smaller. And I have a lot of colleagues that study the electron diffusion region, which really gets into the nitty gritty of how exactly magnetic reconnection happens. So that's one way. Another thing that people study a lot is waves. So plasmas being a fluid have waves associated with them as well. Um, and as they interact, different waves are formed. So that's another thing that people study is using waves as well. You can also look at magnetic fields and electric fields and the strength of those. And that's kind of your bread and butter of how you study magnetic fields. And I guess I do want to mention one other thing too. There's also two different types of, or I guess two different methods of studying space plasmas. There's in situ measurements, which means you're actually there. So MMS is an in situ mission. It's actually there at the magnetopause taking direct measurements of plasma. You can also do remote measurements using, I can't think of a, I know one. It's got kind of a funny name. There is a radio network called SuperDarn that people use to study magnetospheric physics remotely. So that's another way that you can study magnetospheric plasma, either in situ or with remote sensing.
Interesting. Such a weird name for a group. Tracy comments, as a Lehigh alum, I'm sorry you had to reference the distance to Lafayette in your example.
Yeah, go Leopards beat Lehigh. Sorry about that.
Next question. When the North and South Pole change places sometime in the future, say 2023, how will that affect incoming solar wind?
I really have no idea. It'll be very interesting to see. One thing that might give us a clue is studying the magnetic field of Uranus, believe it or not. So Uranus is weird in that it's kind of on its side relative to Earth. Earth is kind of straight up and down, a little bit tilted, and its magnetic field is mostly aligned with its rotation. Well, Uranus is not that way. And that just makes things very interesting. It's got a unique magnetospheric structure. And I don't really know a whole lot about that. But it'll be interesting to see. I know a lot of people have talked about going to Uranus because we've gone to Jupiter. We have the Juno mission. We've gone to Saturn with the Cassini mission. We haven't had a flagship mission to Uranus yet. So that might provide some clues as to what the magnetic environment of Earth is going to look like when the pole flips.
All right. Next question. Does the flipping of the Earth's magnetic poles impact your research?
Not yet, because for my lifetime, the pole is mostly been stationary. I say mostly stationary because it does move a little bit. Indirectly, I actually did another project with some other grad students calibrating an instrument that went on a rocket. And for that particular project, it did actually matter that the magnetic field was moving a little bit because we wanted to shoot the rocket into a very particular region of Earth's magnetic field. And it moved enough that, we had to time it just right. So for now, I didn't do any science related to that mission. That one of my fellow grad students does that, but I did help with the calibration. So the movement of the pole definitely has to do with his research, but my research, not so much.
All right. Are there any other questions? All right. If there are no more questions, thank you so much, Kevin, for your amazing presentation. I know I learned a lot, and I hope everybody else did as well. And to everybody out there in the internet, cheers to the universe.
Cheers. Thank you very much.
We'll hopefully get to see you for our next installment. Thank you so much and have a wonderful night, folks.